Welcome to the 14th video in the mathsonlinetuition.com videos where we go through C1. We've come to the last chapter of C1, chapter 8, integration. And this chapter is something very simple in terms of its content. And I think the main idea is to just introduce you to, again, a very powerful mathematical tool, and that is integration. And so you can see there's only 3 different aims and objectives here. So this chapter is just subtly introducing you to integration and at the same time not overburdening you before you finish C1. So let's get straight into it. 8.1. You can integrate functions of the form fx equals axn, where n is an element of the reals and a is constant. In chapter 7 you saw that if y equals x squared, then dy over dx equals 2x. Also, if y equals x squared plus 1, you saw dy dx equals 2x. So the main theme here is trying to emphasize that if you have a coefficient of a x, then when you carry out the differential process, okay, you will have this particular equation, formula, okay, based off of what we discussed before with multiplying the coefficient and the power, subtracting the power. In this particular case, if dy over dx equals xn, then you're going to have y equals 1 over n plus 1 x n plus 1, okay, plus c. This is called indefinite integration because you can't find the constant. Now the reason why you can't find the constant is because you have no values, for example initial values or boundary values, and we'll discuss all these points later on, but in this particular stage it's called indefinite integration because you have no values to figure out c, therefore you can leave it as such. Example 1. Find y for the following: x to the power of 4. Now I just want to make a very fine point here, and something that's going to help you understand everything very easy. And it is as follows. This here is the reverse, or integration is the reverse of differentiation. And I'm going to draw a nice little, so you have differentiation, okay, gives you integration. And I'll explain to you why. Because these two methods complement one another in the sense that you can go from one of the forms to the other by carrying out that particular technique. So we have dy dx equals x4. Let's integrate this. In differentiation, I'll write this down for you. The first step was what? Multiply the power by the coefficient, and then 2 subtract 1 from the power. And we saw that with dy equals nx n minus 1 when y equals xn, right? But now Well, with integration, it's the complete opposite. So what we do here is the following. We add a number to the power and then we divide it. So it's the complete reverse. So we add 1 to the power and then we divide the power by the coefficient. Do you understand that? So now we would have y equals, so if dy dx equals xn, then y is going to be, well, n plus 1 over xn plus 1 plus c. Okay, so with this example here, we have x4. Well, that is going to mean that we have x4 plus 1 over 4 plus 1, which gives us x5 over 5. And with b, where we have dy dx is x minus 5, well, let's add. So we get minus 4, and then remember we divide. So we have minus 4, and then we have plus c. So we have y equals plus c. Exactly what we have here. Okay. Example 2 goes through a similar thing, just using some more complicated terms, if you like. And again, same thing that we mentioned here. K is the coefficient. K is divided by n plus 1. Okay. Examples for you to do here. You can apply the principle of integration separately to each term of dy over dx. So if you have this equation here, you apply the first, second, third. You can apply integration to each one. So you'll have 6x2 over 2, then you'll have minus x minus 2, and then you'll have plus 2 excuse me, x to the power of 3 over 2 plus c. And again, it's just using the terms of integration, and this is how it's been denoted in this particular situation. Exercises. Now it brings you on to the integral sign. This is the integral sign, and there's a story about the integral sign which I think will help you to remember it, but we'll leave that for another time. But suffice to say, the integral sign is denoted as such, with this dx depending on what the variable is, okay, in our particular situation x, and what's conventionally denoted in many a textbook is the x as well, so we'll stick with that. The integral of x to the power of n, okay, with respects to the x, will give you x n plus 1 plus c. Okay, so here it's asking you to integrate this, and you can see it's very simple. They've just introduced this equation in this particular form, and now you integrate each part, integrate this part or term, and then add the plus c. So it's very straightforward. We'll do d very quickly. D is the integral of 4t squared plus 6 dt. So we add 1 to the first power, and then we divide it, plus 6t plus c. There we go, very simple. More exercise for you to do. You need to simplify an expression into separate terms of the form x to the power of n before you integrate. So what this is essentially telling you is you need to simplify everything first before you can carry out integration. And the reason is as follows. Let's take question B. X squared plus 2x. If you integrate this, okay, and you integrate this, there will be more of a headache when it comes to resolving the integral of this and the integral of this multiplied together. And sometimes I believe that's not always the right answer. So let's show you an example. x2 over 2, x3 over 3, plus 2x minus 2 over 2, cancel. Now we'd have x6, so now x5, 6 bottom, plus x0, which will give you 1. So I have x5, 6. So you can see that this is the step that we've taken by multiplying these out. But that's not actually the right answer, because if we were to do the conventional way, we would have x3 plus 2. If we integrate this, it's 4 plus 2x plus c. Now this is the correct answer. And you can see that these two different answers leads us to suggest that simplification is vitally important in order for us to get the right answer. So we have to carry out the simplification. Here this needs to be changed to 1 over 2 and this expanded out, and likewise here the same thing, simplified. More exercises for you to do. You can find the constant of integration c when you are given a point xy the curve the function passes through. So here is a point 45. Now you have the answer integrated c. You know what 5 is because it's y, and you know what x is, which is 4. Remember we said before that fx equals y, and then we have a point P at 4, 5, where this is x and this is y. So you can say 4, 5. Well, when you have fx, and in this particular situation it's 2 over 5 x to the power of 5 over 2 minus 4x to the power of a half plus c. Then you plug in the 4, you know it's equal to 5. Okay, you get 2 over 5, this is 4, 5 to the power of 2, 5 over 2 minus 4, that's 4 half plus c. 5 equals, figure this one out, you can see that we have 65 over 5 minus, this is 2, 8 plus c, so we get that c equals 1 over 5. Okay, that's the answer. So here, if we were to go back to our equation, we can put 1 over 5. Okay, and this is the equation of the curve. Here's some exercises with some points for you to do. All you need to do is integrate. Once you have that plus c, here you have the point to figure out that c. And here you can see that we have mixed exercises and a summary, a very brief summary. So literally all the summary was just giving you that formula here represents dy over dx. Alright, and then you have the k as being the coefficient, and then again what we've just most recently gone over, the integral sign. okay, and the C, and then of course again if we have the point we can figure out what C is. So that brings us to the end of C1. I hope all the videos have been helpful up to this point. Please do bear with us as we decide how to progress from this point onwards. Naturally we would go to C2, and we will do. However, we're also trying to understand what optional modules to discuss as we go along. Naturally you will be doing this simultaneously alongside your core modules, so please do bear with us, and we hope to see you next time for our C2 module. Thank you, goodbye.